In all the examples that we've done so far in which we've applied Hamilton's principle or the equivalent Euler-Lagrange equations to a dynamical system, we've always written our Lagrangian in the minimum number of dependent variables possible. That's the degrees of freedom. So we've determined the number of degrees of freedom at the outset, and we've written the Lagrangian in terms of that number of dependent variables. So Q1 through Qn, where n is the number of degrees of freedom. There are situations where that's not necessary. In fact, there are situations where it might actually be easier to do it a slightly different way. So I want to do two examples in this video to show us how that can be done. Obviously, in the end, you get the same solution, but it's going to use some of the techniques that we've developed in Chapter 2 and apply them to these dynamics problems. So as I said, in the past, when we formed our Lagrangian, we would eliminate any other variables other than those necessary to specify the state of the system, our n degrees of freedom. And one of the nice aspects of using Hamilton's principle that we've seen is that it's actually not necessary to determine the forces of constraints that act on the system. And the reason for that is because they don't do any net work. If there's no net work, then we don't have to include it in Hamilton's principle. Now, instead of eliminating unnecessary dependent variables greater than n, the number of degrees of freedom, we could say we know we have n degrees of freedom, but what if we have k additional constraints? So that would mean we have n plus k dependent variables. N of them are necessary, and there's an additional k that aren't necessary, but we're going to include and then have constraints that take care of the relationships between those extra variables and the others. So now q goes from 1 to qn plus k, and we have k algebraic constraints on those generalized coordinates that take into account the physical geometric constraints that are applied to the system. Now, I want to show you how that's done. First, we're going to do a familiar example that we did back in Chapter 4. So this is where we have a mass that's on the end of a massless rod of length L hanging from the origin. It has an angle alpha from the vertical axis of rotation, and it's rotating about that axis with an angular velocity of capital omega. Gravity is down. So we've done this problem before, and you may remember from the earlier video where we did this problem, we discussed ad nauseum whether to use alpha, y, or r as the dependent variable. We recognized it was axisymmetric, that we only needed one dependent variable. It's a 1 degree of freedom system, but we couldn't decide between r, y, and alpha. Now there's some advantage to that. You just write down your t's and v's as necessary using either of those variables, whatever makes sense, and then at a later stage, before you apply your Euler-Lagrange equations to the Lagrangian, you decide which one you're going to use. So there's still some advantage, but we can even go one step further. So let's reconsider this problem, but now using a constraint. So this is the Lagrangian, the t minus v that we got in that previous example, 1/2 m cap omega squared times r squared. That's obviously the kinetic energy due to the rotation of the mass, minus mgy, which is the potential energy due to the elevation of the mass. And you see we have two dependent variables, r and y. It's truly a 1 degree of freedom system, so we need one constraint that relates these two variables together. Well, that's straightforward. That just comes from the geometry. It's just a triangle, so r squared plus y squared is equal to l squared. So we're going to keep that as a constraint, whereas previously we used that to eliminate the r variable. Now we're going to keep the r and the y variables in our Lagrangian and impose this additional constraint that relates the two together. So of course we do that using the Lagrange multiplier. So here's our L, t minus v, and then the augmented Lagrangian is the Lagrange multiplier cap lambda times the constraint. Now remember, because this is a geometric or algebraic constraint, we have to allow for the Lagrange multiplier to be a function of our independent variable, in this case time. So now we have L tilde, our augmented Lagrangian, and now we just follow through like we normally would. So we have 1, 2 variables. So we have two Euler-Lagrange equations, one for r and one for y. So in the previous case, we only had one because we had already eliminated one of the variables. We only had one variable left. Now we have two variables, so we need two Euler-Lagrange equations. When we evaluate this first equation, we get this. And if I solve for lambda, because normally we want to eliminate the Lagrange multiplier because I actually don't really care what it is. So if I solve for lambda, that's minus a half m cap omega squared. Okay, so that's from the first equation. Now let's take a look at the second equation. From the second equation, we do the partial derivatives, and we get this expression as our second Euler Lagrange equation. Now I could solve, for example, for y. Y is mg over 2 cap lambda. Well, we have lambda from this expression here from the first equation, so I can substitute that in here and get an expression for y. And that's just minus g over cap omega squared. And as you'd expect, that's the same answer that we got the previous time we did this equation the other way. So obviously both are equivalent mathematically. One may be a little bit easier in some situations than another, but I just want you to be aware of this possibility of doing them this way. So let me make a few comments before we do another example. So in this case, you'll notice we had two Euler Lagrange equations because we had the two variables, and then we eliminated the extra variables using those Euler Lagrange equations rather than eliminating the additional variables before getting the Euler Lagrange equations as we did previously by substituting the constraint directly into the Lagrangian. Now there is one reason why you may want to do them this way, and that's because the augmented Lagrangian now has this additional term. This term corresponds to the potential energy due to the force of constraint. So if you did want that force of constraint, this is the potential energy that results from that force of constraint. So there are situations where that may be helpful. Okay, so let's do a second example. In this case, we went to Bed Bath & Beyond and we bought a parabolic bowl. So y is equal to x squared. We're going to let the mass go back and forth in the bowl without friction. So if we think about the number of degrees of freedom, what is the minimum number of dependent variables required to fix the state of the system? Well, if I know x, if I know where I am on the x-axis, because it's sitting in the bowl, I know y as well. So I only need to know x, and then y is given from this relationship, and so it's a 1 degree of freedom system. So Q1 will simply be x as a function of time. So let's do this both ways. So first we'll take into account the fact that we know this is a 1 degree of freedom system, and we'll reduce it down to that one dependent variable. So we know that y is equal to x squared. So if I have a y dot, so a dy dt, from the chain rule, that's just 2x x dot. So just differentiating y in case we need it. Then Lagrangian, t minus v, t is 1/2 m times the quantity x dot squared plus y dot squared, and v is mgy. Always remember, as long as y is up, then v is plus mgy. So here's our y dot, so we can substitute in the 2x x dot for the y dot and square it, and that's here. Factor out an x dot to simplify the Lagrangian a bit, and you have this expression here. Now you'll notice we only have one dependent variable, x, 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 no y. So we've already taken into account that we know this is a 1 degree of freedom system. We've substituted the constraint into the Lagrangian to put it in the form of one dependent variable. And now we just follow through the usual process. So we take the partial derivatives that are contained in the Euler Lagrange equation, of which there are only one because there's only one dependent variable. We substitute those in. We take the derivative ddt, which requires some product rules, and we simplify it down a little bit using some algebra, and we get this expression. So you'll notice it's a second order, highest order derivative is 2. It's nonlinear, because notice we have an x squared times an x double dot, x times the square of x double dot. So these two terms are nonlinear. So a second order nonlinear differential equation, which we'd have to solve numerically. But let's take a look at this, the alternative approach. So we get our Lagrangian, same Lagrangian as before, t minus v, but I'm going to keep the two variables x and y, the two dependent variables x and y, and we'll incorporate the fact that y is equal to x squared as a geometric or algebraic constraint. So we form the augmented Lagrangian, t minus v, that's the original Lagrangian, plus the Lagrange multiplier times the constraint, y minus x squared. Doesn't matter whether you say y minus x squared or x squared minus y, you'll get the same thing. So we have two dependent variables, x, y, and x dot and y dot. So the corresponding Euler Lagrange equations, one for x and one for y. You evaluate those to do all the partial derivatives, and the first one gives you this, and the second one gives you this. These are the two equations for x and y that we need to solve. So now, because we haven't incorporated the constraint before we got the Euler Lagrange equations, we now have to eliminate the lambda, the Lagrange multiplier, using the Euler-Lagrange equations themselves. So we can do that. We can multiply the second equation by 2x, and then just add the two together. That will get rid of the lambda term, and you end up with this expression here. Now again, involved both x and y. So if we differentiate the constraint, y is equal to x squared twice, we get this expression in terms of x, substituted in for y double dot, and we get this expression here. Simplified a bit, and we get the same equation of motion as we had using the other technique. From both of these examples, you can see there's not any inherent advantage in doing it one way or the other, just two different approaches to solve the same problems. In these cases where we have geometric constraints that are applied to the system, either one works fine and gives you the same answer. And here's an example. So if you rotate this, that's the mass rolling back and forth in our Bed Bath & Beyond parabolic bowl. Now, just as was the case in the previous example, this additional term in the augmented Lagrangian that includes the constraint, that is the potential energy due to the force that's required to keep the mass within the bowl. So again, we didn't have to think about that. We didn't do a free body diagram for the mass, so we didn't have to figure out what was that normal force acting on the ball to keep it in the bowl, whereas that would be the case if you were to use Newton's second law, draw the free body diagram for the mass, you would need to include that constraining force. Now that may bother you, but let's think about why that is in the context of energies and works. So the constraint itself, there is no virtual displacement in the direction of the force. The force is acting normal to the parabolic bowl on the mass, but it's moving tangent to the bowl. So the movement and the force are orthogonal. So there is no force times a distance. Therefore, there's no work being done on the mass by the constraining force. And this is the case for algebraic constraints, which our dynamics friends will refer to as holonomic constraints.